Hello, how are you? Uh, in this video, we are going to learn how the TCP multiplexing work, which is the concept of sockets. Then we are going to see some examples on TCP multiplexing in terms of different connections between clients, servers, which is the process to create a socket, how many connections and sockets are involved in a particular situation. And finally, we are going to see a specific command called netstat to know how many TCP connections are in our computer. So the concept of multiplexing is used to connect the transport layer with the application layer to know which is the application protocol that is related to a specific transport protocol. Multiplexing is carried out by means of ports. So if you remember, the length of a port is 16 bits. So we have a range of from 0 to 64 kilobytes, 65,535. This is the maximum number of a port for source port or destination port. For example, if I'm going to connect with a destination host, the source port will be a specific number for my computer, and the destination port will be related to the application that will be run on the destination host. So at the end, a port refers to the application layer process of the packet, both at the source side or at the destination side. Then we introduce the concept of socket. The socket is the combination of an IP address and a port. So in this example, we have a socket that is composed of this IP address and this port. Okay, and we separate the IP address from the port by means of a semicolon. Since this is the range from 0 to 65,535, there is a portion of this range that is reserved for specific applications. So these services are called well-known ports, and the range is from 0 to 1023. So in this range, the numbers are reserved to ports to know which specific application we are talking about. For example, port 80 refers to HTTP. Port 21 refers to FTP. This is another protocol for file transfer. What else? Port 23 refers to Telnet, and there are several numbers reserved to specific applications for the ports. In this table, we have an example for well-known ports. So in the first column, we have the type of protocol, the service. In the second one, we have the number that is reserved for such application. And the last columns refer to the transport protocol they are based on. For example, the first case, we have the datetime. It's a protocol for retrieving the time from the system. So port 13, and it runs on top of UDP. Since it's a periodical protocol to ask for the time, so maybe it doesn't matter if some of the packets are lost. So this is the reason why it runs on top of UDP. We are requesting the time after a while, so it doesn't matter if a packet is lost. On the other hand, if we look on the next protocols, for example, FTP that runs on top of TCP, SSH, Telnet, all of them run on top of TCP, because on these application protocols, we want that all the data arrive correctly to the destination. FTP is a protocol used for file transferring messages or documents. Telnet and SSH are protocols for remote control, remote login on remote computers. The difference is that SSH is secure and encrypted, and Telnet is based on plain text. SMTP, it's a protocol for emailing, and it runs as well on top of TCP. DNS is a specific particular case. You can see that it can run on top of both TCP and UDP. So in a normal situation, DNS is invoked from my computer, this host, DNS server, to ask for a specific IP address. I'm giving the name, I'm requesting for the IP address that is associated to that name in order to be included in the IP header. So this communication from a host to a DNS server is commonly based on UDP. But if the DNS server needs to communicate with other DNS servers, in this case, DNS runs on top of UDP. That's the reason why we have both options in this case. What else? POP3, for example. POP3 is an email application protocol that runs on top of TCP, HTTP, and the secure version as well. We want that all the data arrives correctly to the destination. This protocol, SNMP for network management, that runs on top of UDP. So at the end, we have a very big range of numbers for ports, but the first portion from 0 to 1023 are reserved for specific applications. In this URL, you have a list of the combination from ports and protocols, and we have to think that a TCP connection is defined and specified by two sockets. One socket at the source device, source host, and the other socket referring to the destination host. So a TCP connection is specified by two sockets, but at the end, it is defined by 4 different values: 2 IP addresses, source and destination IP addresses, and 2 ports, source and destination ports. If we think on 2 TCP connections, at least one of the 4 values must be different, because if all the 4 values for 2 TCP connections are the same, we are just talking about one TCP connection. In this slide, I'm going to show you an interactive animation about the TCP multiplexing concept, and at the end, multiplexing on the layers of the TCP IP stack. As you can see, the physical layer has been removed. We start from the link layer, considering that we have a frame, for example, with Ethernet technology. At link layer, we have a header of Ethernet type, and then the payload, which is an IP datagram, and finally we have the CRC for error checking. So in this case, if the IP datagram is passed to the next layer in the stack, the network layer, the IP datagram, as you know, has an IP header and a payload. How to know which is the type of the payload? By means of the protocol field. Protocol field is equal to 6. It means that we can find a TCP segment in the payload. Then we have a checksum as well. So at link layer and at network layer, we have both fields referring to checksum. If we go up from the network layer to the transport layer, the TCP segment format is as follows. You have the TCP header and the data, the payload, as usual. How to know which is the specific type of data we have for the transport PDU? By means of the destination port. It's like a protocol, but this destination port tells us which is the type of application protocol that is encapsulated inside the application data, inside the payload. So in this case, we have a telnet application, But otherwise, if we have 21, we have a different protocol, which is FTP, or 22 SSH. So depending on this number, we have different application data. If we look at the left of the stack, we have that we have two different instances depending on the transport layer we are talking about, TCP and UDP. And finally, if we move the application data, the payload of the TCP segment, in this case, to the application layer, we will have the application-specific message, the telnet message in this case. If we had destination port 21, FTP 80, HTTP, so these numbers we have been seeing in the previous slide, in the previous table. So at the application layer, we have multiple instances. We have many protocols at the application layer that must be multiplexed by means of the destination port at transport layer. Just to finish with this slide, we can see that there is a field for error control both at the link layer, IP layer, and transport layer. This is one of the reasons that when migrating to IPv6, they decided to remove the checksum at layer 3. So they thought, if we have checksum checking at transport layer and Ethernet layer, maybe it's not necessary to also include in the IP header, in order to reduce the time for processing this checksum. In the following, we are going to see several examples of TCP connections and of sockets under different situations. So in this first scenario, we have a client on the right with an IP address and a server on the left with another different IP address. This server is a web server, so it is listening at port 80. So the socket at the server side is this one, IP address and port 80. Imagine that the client wants to run a web browser. A port is assessed in order to create a TCP connection. This port is a source port, so the limitation is that we cannot use a source port with a number that is below 1023. So remember that we have this range that is reserved for the destination port for a specific application. So in this case, we need a bigger number for the source port. So the socket is created, the composition of IP address on the source port, and then the TCP connection is established and identified by means of two sockets. At the end, 4 values, 2 IP addresses and 2 ports. So we have 1 connection and 2 sockets. Moving to other example, in this case we have 2 different servers, web servers. The first one is this one and the second one is this one. And we have only 1 client. And the client wants to open a couple of browsers in order to access a couple of different websites. So in the first case, the computer runs a web browser toward the server number 1. So the source port is, for example, 1038. So it's not necessary to have the same number always. So we can have a different source port. The socket is created and then the connection is established and identified by means of the 2 sockets. At the same time, we can run another different web browser toward that server number 2. For example, imagine that for server number 1, we are going to access elpais.es. And for server number 2, we're going to access to elmundo.es, different web servers. So in this case, I open another web browser. and type elmundo.s, I will have a different port, different sockets. In this case, this socket is different to this one by changing the source port, and then the TCP connection is established and identified by thanks to the two sockets. So in this case, we have 2 connections and 4 sockets. Next example, we have a web server that is listening at port 80. This is the web server with this IP address, this socket. And the web server wants to allow different requests from many clients, for thousands of clients. So I'm open to have different requests from different clients. In this case, we have 2 computers, this one and this one. So the PC number 1 runs a web browser as usual. It has a source port, socket, and then TCP connection. And the other one will have maybe the same port or maybe a different port, it doesn't matter, with a specific socket and then another TCP connection. So this socket, this one, has 2 simultaneous connections, but not 2, maybe thousands of simultaneous connections. Imagine online journal. Everyone wants to access it, so we have many requests. In this case, there are 2 connections because of the IP address of the client. The difference is that in this case we have only 1 socket. In this case we have 2 sockets that are different because they are different computers. 2 connections, 3 sockets. In this example, we have a server that is both web and POP3. POP3 is a protocol for mailing, for email. So in this case, this machine is able to provide web content as well as act as a email server. So we have in the same machine, the big machine, the server, 2 sockets. Socket number 1 referring to the web, socket number 2 referring to the email. This is a typo here because 100 refers to POP3. Well, so my client wants to access the web server as usual. I have a port, socket, and a connection as usual, but I want to also access to the mail server. So I can open, for example, an Outlook, an email application toward the same machine. Then I will have a different number of port, different socket. In this case, the difference is the port because we have the same IP address since it is the same computer. And we have another different TCP connection. In this example, we have 2 connections and 4 different sockets. Going back to the same example as the previous slide where we have a web server, port 80 is listening, and this is the socket, maybe I can have the possibility of accessing several times toward the same web server. For example, in this case, I run the web browser, I have the port number 1038, I have the socket and the TCP connection, but I can open a different web browser. For example, I was running Chrome and then I was thinking to move to Safari or to Internet Explorer. No, I'm joking, Internet Explorer never. Firefox, and then I can access to the same machine using a different source port, 1039, and then a different TCP connection. In this case, we have 2 connections and 3 sockets. 3 sockets that are divided in 2 at the client side and 1 on the server side, listening to incoming TCP connections. And finally, this is the most complex scenario where we have 2 different servers and they also want to connect the other as a client. I mean, on the server on the left, we have a web server installed, okay, port 80. On the right, we have also a web server installed. Port 80 is listening. We have the sockets in both cases. And, for example, the machine on the right wants to access the web server on the left by acting as a client. So it can also work as a regular client, a regular laptop or PC. Source port 1038, socket, TCP connection. But at the same time, the server on the left will want to do the same. Run a web browser toward the one on the right, port 1038, socket, and connection. In this case, we have also 2 connections of 4 sockets. And they are different connections because they do not share any socket. So they are differences. In this case, the difference is the port, and here also the port. So finally, we are going to introduce a command called netstat to be able to know how many TCP connections we have in our computer, the state of each of the connections, which is the other host that is involved, and so on and so forth. For example, if we want to know which ports of our machine are in listen mode, we are listening about, for example, port 80, if we are a web server, we can use this netstat to be able to know if our computer is working as a firewall to block unnecessary ports or to drop packets we don't want to traverse through our network or our computer. So let's see an example of execution of this netstat command. Imagine that we have type netstat -n in our terminal. If we don't use -n, the command will give us the possibility to see names and both at the IP addresses, if we have the access to the DNS server, and related to the ports. For example, POP3 instead of the value 110, which is the number of the port. So as output, we have in the first column the type of protocol. It's always TCP. Second column is our local address, the information about our computer. The third column refers to the other host of the specific TCP connection. And finally, the last column is the state of the connection. So let me go from bottom to up in the list. If we look at the last row, we are seeing that we have a state listen. It means that we are listening on a specific port. If we go to the second column, which refers to our local computer, and we can see that it's an asterisk and 80, it means that my port 80 is in mode listen, and I will accept incoming requests to any of my IP addresses and listening on port 80. From where? From any IP address and from any source port. So at the end, I'm acting as a web server, and I will accept any request from any computer in the world and with any source port. If we go up, we can see that these 2 rows, these 2 TCP connections are established. So the TCP connections are sending data. So if we go to our local address, we can see that they refer to the web server I have installed in my computer. This first one refers to one of my IP addresses, and the second one refers to the second IP address. Which are the other hosts that I'm connected to? So the first one has this IP address and this source port, and the second one has another different IP address and this other second port. So as a summary, I'm acting as a web server. I'm accepting any request from any IP address in the world. And at the moment, I have two TCP connections that are established. One from the client ending in .40 and the other one ending in .30. If we go up, we can see there is a different state in the second and third rows. This different state is time wait. That means that I have the connection, but we were trying to disconnect. It's a kind of a state between established and closed, which means that the connection is already closed. So these connections are waiting to be closed in this host. Okay? Now we can see that in my local machine we have port numbers above 1023. So it means that in this case I'm not acting as a server, but as a client. A client of what? A client of a POP3 server. And this server has this IP address. And I have two different connections to that POP3 server. Finally, the first row refers to an already established TCP connection, and again, I'm acting as a client to a different service, FTP, with this IP address. And this is how we have to understand this command. Now, I ask you to create a network diagram like the ones we were commenting in the previous slides, but for this example. So you have to create the local machine, these ones, the remote machines, these ones, and saying which type of server, FTP, POP3, the IP addresses, the sockets,